I'm going to do a video about Euler's identity and formula, which are super important because they connect seemingly unrelated areas in math together in one beautiful equation and identity, I guess. So it connects Euler's constant, E, imaginary numbers, and trigonometry, sines and cosines. That's what Euler's formula does. And Euler's identity connects the very important numbers 1, I, pi, e, and 0. So I'm going to start by giving you Euler's formula. E to the ix equals cosine of x plus I sine of x. As you can see here, we have e to the ix, e to the power, which has e in it, I times x, x is whatever number you want, and I is for imaginary numbers, and cosine of x plus I sine of x. And cosine and sine are from trigonometry, so it connects imaginary numbers, e to the power of something, Euler's constant, and trigonometry all in like one equation. And for the right side of the equation, since cosine of x and sine of x are both going to be real numbers, the right side is going to be an imaginary number always. So e to the ix is always going to be an imaginary number. So I'm going to use this formula to find Euler's identity, which you just get by plugging in x equals pi. This formula for x equals pi is just called Euler's identity. So you get e to the I pi equals cosine of pi plus I sine of pi and that equals cosine of pi is -1 and sine of pi is 0, so I times 0 is 0. E to the I pi equals -1. That is Euler's identity, but the more common form is if you add 1 to both sides of the equation, e to the I pi plus 1 equals 0. And typed up for you, that's the identity, and typed up for you is right there. E to the I pi plus 1 equals 0. This is super important because it connects 5 super important numbers all together in one identity. E, Euler's constant, which is useful in like calculus, natural logarithms, and finance. I, which is for imaginary numbers. Pi for trigonometry and geometry. And 1 and 0, which are super important. I don't need to tell you, they're like amazing. They have so many properties. So let's do some examples. Also, 2 more things I wanted to mention is that E, Euler's constant, is about 2.7182818, and it's irrational, so it goes on forever, but this is a good approximation. And to find the exact number where you get E from is the infinite sum from n equals 0 to infinity of 1 over n factorial. If you do 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial and all the way to infinity, you'll get E exactly. So let's do 2 examples. First, verify that e to the 0th power is 1 using Euler's equation. Okay, so I'm pretty sure that they knew that e to the 0 would be 1 before Euler came out with this, but still it's good to like verify that it all makes sense. So we're just going to plug in that x equals 0. So e to the I 0, I times 0, equals, this is the same thing as e to the 0, so I'm just going to write equals e to the 0 equals, because I times 0 is 0, cosine from Euler's formula of 0 plus I sine of 0. Just plugging in 0. So I sine of 0 is 0, so I times 0 is just 0. And cosine of 0 is 1. So equals 1. Same thing, I'm just going to write it here, equals e to the 0. Sorry, that just looks like a dot. E to the 0. So this proves that it does equal 1, and Euler's formula does make sense for x equals 0. So let's do another example. Find e to the ith power. Okay, so e to the ith power, we're just going to plug in x equals 1, so then we just get e to the I. So e to the I would just be for x equals 1. Just going to plug in x equals 1. E to the I equals cosine of 1 plus I sine of 1. Okay, so this is not, these aren't like clean numbers like the other ones were. So this is equal to cosine of 1. That is a really long number, so it's about 0.54. And sine of I is about 0.84 plus 0.84 times I. So this is the answer, 0.54 plus 0.84 times I. Sorry, you can't really see the I there. Okay, so 0.54 plus 0.84 times I is e to the ith power using Euler's formula. That's pretty much it. Thank you for watching. Bye.